Stationary waves on a stretched string. In this video we will discuss about the theory and practical aspects about the stationary waves on a stretched string. A wave is the propagation of a disturbance through a medium. A wave can be described by its basic properties, which are amplitude, wavelength, frequency, and period. When a vibrating body produces waves along a tightly stretched string, the waves are reflected at the end of the string, which causes the two oppositely traveling waves to exist on the string at the same time. These two waves interfere with each other, creating both constructive and destructive interference in the vibrating string. If the two waves have identical amplitudes, wavelengths and velocities, a standing wave or a stationary wave is created. The animation shows two waves moving through a medium in opposite directions. The blue wave is moving to the right and the green wave is moving to the left. The blue wave and the green wave interfere to form a new wave pattern known as the resultant. The resultant in the animation below is shown in black. The resultant is merely the result of the two individual waves, the blue wave and the green wave, added together in accordance with the principle of superposition. The standing waves are not propagating, but they are superposition of propagating waves, therefore the frequency, f, and the wavelength, lambda, satisfy the relation, v equals f lambda. The velocity of a transverse wave on a string that has the mass per unit length, m, and is under the tension, T, is v equals square root T over m. Let the length of the string be L, and if the standing wave has n number of antinodes, then, L equals n lambda over 2. Combining the above relations we get, f equals n over 2L into square root T over m. Let's observe the above relationship using a practical setup. Following are the apparatus for the practical sonometer. The sonometer is a long hollow wooden box along the top of which are stretched one or more strings rigidly attached to the box at one end, with provision at the other for changing the tension. A wire sine wave generator, a signal generator, is used in this practical to generate sine wave with specific frequencies. A loudspeaker, a weight hanger and weights and a pulley is also used for the practical. For the practical, one end of the wire is connected to the speaker and the other end is applied with a load of 20 grams, to provide the tension for the wire. The loudspeaker is connected to the signal generator and provided with a sine signal with the calculated frequency. Since we are not changing the tension, mass per unit length and the length of the wire during the practical, frequency is directly proportional to the number of antinodes. The setup is ready. We have generated a sine wave with a frequency of 82.47 Hz in order to observe 3 loops on the wire. The signal is given to the speaker and passed to the wire. You can observe antinodes, nodes on the wire resulted from the stationary waves. Let's observe another pattern by changing the frequency. Varying current to the wire, and a magnetic field perpendicular to the direction of current using a horseshoe magnet. Therefore, according to the Fleming's right-hand rule, the wire will move in the horizontal plane, as you can observe. Standing waves can be observed in physical media such as strings and columns of air. When a wave traveling along a medium and reach the end, it will reflect back. This effect is mostly used in musical instruments where, at various multiples of a vibrating string or air column's natural frequency are used to create standing waves, allowing harmonics to be identified. Thank you for watching.